Okay, this is an optional lecture. I'm going to do a couple more Newton's third law problems, just because I find them fun. And then I'm going to talk about non-inertial reference frames and fictitious forces. All right. Let's consider tension in a string again. But now let's justify the idea that the tension is uniform throughout the string, if the string is massless, which we've been assuming. For as an idealized string, the tension essentially acts as a conduit that allows forces to be transferred from one end of the rope to the other. And you don't have to worry about the mass of the string itself kind of taking up some of that force. My hand-wavy version of this is that you could think, well, if the rope has no mass, then it requires no force to accelerate it, because the acceleration you need for a given mass is related by F equals ma. If m is 0, then you don't need any force to get whatever acceleration you want in the rope. Let's actually now just try to think about this. So let's have a block. I'll call it mass block. But then I'm now also going to give the rope some mass as well. And we're going to analyze this and assume that I pull on one end of the rope with some force. That causes the entire system to accelerate. How does the mass of the rope play a role here? Now, with a massless rope, we would have said, okay, this sets up a tension in the rope. The tension is equal to F in this case. And so the block feels a force acting on it that is the same magnitude and direction as F. You know, examples we gave where you were pulling boxes at an angle or with ropes and sleds and whatnot was all kind of working this in. So the two systems I would identify in this case is the rope and the box. So for the rope, you're pulling on the rope with some force F, but then the rope is also touching the block, so there's some F block that is pulling back on the rope. Then in terms of the box, it is just feeling the rope pulling on it, so I'm going to call this T end. The tension at the end of the rope that's really close to the box, not the part that's really close to my hand. Now, and vertical forces be damned. So in this case, the identification to make is that these two forces are Newton third pairs. So that T end is minus F block. Again, those are the 2 points of contact, like two things pushing on one another or pulling on one another. The directions are opposite. If we look at the block, some of the forces on the block equals the mass of the block times the acceleration of the block. I'm just going to, if everything has the same acceleration. This implies that what is acting on the block? Well, we said T end is acting on the block, and that equals the mass of the block times its acceleration. All right, and then the rope, sum of the forces equals the mass of the rope times its acceleration. We can write down that there's the force of the pull plus the force of the block, and that equals the mass of the rope times the acceleration of the rope, which again is just A. I want to combine these in some way. So I'll make the realization that by Newton's third law, the tension is minus F block. So this is M block acceleration. And then if I combine these expressions, that says that the force of the pull is minus MBA equals M rope A. I believe that is all well and good. Let's see, but what do I want to actually solve for? I want to actually write this in terms of T end. So let's see where I get from. Yeah, I actually want to write this in terms of T end, I'm sorry. So I'm going to say, I'm not going to substitute it, and I substitute too quickly. So by Newton's third law, so not by this, let me subtract, get rid of this. But it's really more by what we have right here. I plug that in here. But then the force of the pull minus T end. Yeah, the reason we want this is that, remember, this F here is the force that's being exerted on the right-hand side of the rope, where T end is the force that's being felt on the left-hand side of the rope. And this equals the mass of the rope times the acceleration. But now this, I'm going to use the other expression we had above. So actually, this ended up not being useful. But now I'm going to pull from this expression and substitute in to get rid of A, where I'm going to write A as T end over mass of the block. There we go. This is what I'm looking for. So then this says the force of the pull, if I move T end to the other side, is 1 plus the mass of the rope divided by the mass of the block times T end. So what the rope is feeling on the right-hand side, F, is related to what the rope is feeling across the rope on the other side, T end. But notice it's an expression where it's 1 plus this ratio of the masses. However, if we look at this term, if the mass of the rope is 0, or the mass of the rope is much, much less than the mass of the block, then the mass of the rope divided by the mass of the block is essentially 0, if not identically 0. Right? You have 1 divided by 1,000,000. That's an incredibly small number, pretty close to 0, for example. So that justifies it. So if mass of the rope is incredibly tiny relative to the block, or as we just assume it's idealized and massless, then the force that is felt on one end of the rope is the same as the force that is on the other end of the rope. What we said. Essentially, the rope acts as a conduit where you pull on the rope on one side, that creates a tension. The magnitude of that tension is uniform throughout, and the tension on the other side of the rope is equal to that force that you were pulling with. In a sense, you could think of the rope. Well, actually, I'm not going to say that because that builds on a misconception that I talked about when we started Newton's laws. So essentially, this allows us to say that if you create a tension in a rope through a force, right, that tension is uniform throughout and transfers across the system. For example, right, suppose you have a cord that is trying to accelerate you upward at some acceleration A. And we'll say M is the combined mass of you and the elevator car, for example, or the car that you're in. To accelerate you in the car up at some acceleration a force of F equals ma is required. Greater than ma is required, because if we were to do a free body diagram, there would be some force pulling up on the wire, but then there's the weight, your weight pulling down. In order to have an overall acceleration going up, if I define up as positive, F must be big mg plus big ma, pointing upward. I think we did a problem like that in the in-class section. So the force that needs to be applied is not just your weight, but then also the mass times the acceleration. Now take this case, which I think this is called a Bosun chair or a Bosun chair. The car is attached to a cable that goes up around a pulley or around some sort of frictionless, knob or something, and the rope comes back down. And you reach out and pull down on the rope and use that to pull yourself up. You could ask, how much force do you have to apply to make yourself accelerate upward at a certain rate? Or even maybe just the case of just going up at a constant velocity. Well, let's do the general acceleration case first, then we just set it equal to 0, and that would be for the constant velocity. And let's again assume your mass is m. The rope we'll take as an idealized rope, so there it is massless. So in this case, there are two systems. There's you in the car, and then there's the rope itself. You are in contact with the rope is in contact with you. We need to consider that because of Newton's third law. With the rope, if you are doing this in order to make yourself climb up, you are exerting a force, you're pulling the rope downward, so I'll call that just F. That corresponds to the force you are applying to the rope as you pull it down in order to lift yourself up. The rope, of course, creates a tension in the rope as a result, as long as you pull down on it. And we could think, just by looking at the system, this is all vertical. So if I define, and I will define up as positive, if the sum of the forces equals the mass of the rope times the acceleration of the rope, but we're saying that the mass of the rope is essentially 0, then this is saying that this establishes a tension in the rope. The tension points up, the force of your pull points down, that equals 0. This establishes a tension in the rope that is equal to the force you are exerting on it, but in the opposite direction. There's a balance between them. In this case, a result of the fact that the rope doesn't have any mass. Now let's look at the free body diagram for you. Your weight is pointing downward, of course. The car itself is attached to the rope, so there's some tension forces pointing up. But now I have to be careful because, remember, the idea here is that you look at everything that is touching the system. And your hands are reaching out and touching the rope that's dangled off the other side. So your hands are in contact with the rope as well as the cable car being in contact with the rope. So I could do another arrow pointing up. I could say this is the force of, rope on hand. You are touching the rope, therefore there's a contact force between the rope and the hand. So there are three forces acting on you now. The you plus the car. Now the realization is that by Newton's third law, the force you are exerting by pulling down on the rope is therefore the opposite of rope on hand. You pull down on the rope then pushes up on you by Newton's third law. And then we also, from the previous Newton law equation above, also know that the tension has a magnitude equal to the force that you are pulling on. So then for u, we could write sum of the forces equals the mass of u, we've been using capital M, times your resulting acceleration. Now there's gravity, there's tension, and then there's rope on hand equals your mass times your resulting acceleration, which we want the acceleration to be, we know it's going to be pointing, we want it to be pointing up. Next step, Newton's third law can come into play here. So I can replace rope on hand with that is the same as minus your force exerted on the rope. So this is the Newton third law step. Now I can bring in the coordinate systems. And I have to be careful. So it's minus mg because gravity points down. The tension is pointing up, so I expect a positive number. But I know its magnitude is equal to F. We solved that already in the previous Newton law problem. And then I have minus the vector force of your push or your pull on the rope. You are pulling down on the rope, so this is minus F because the vector of your pull on the rope was downward equals mass times acceleration. So then look at what we get. In this case, it looks like it is 2F minus mg equals ma, or the force is mg plus a, looks familiar, but divided by 2. Let me put them both on the same screen. So before we had, where's my highlighter? Before we had said that the force to lift just the cable car and you by one cord was mg plus ma. That's how much force was needed to lift you. But now if we do it instead where you have the cable thrown over a nail or something and then you pull down on the rope that is lifting yourself up, the force that's needed in that case drops by 2. By Newton's second law, by you pulling down on the rope is also pushing up on you with the same force you're exerting on the rope. The rope is helping you push yourself up. And then in addition, there's the tension of the rope, which is also pulling you up. So the rope is kind of doing double duty in this case by Newton, because of Newton's third law. I cannot hear you, but I assume that there's applause going on right now. Newton's third law. What a treat. One more. Suppose I have another one of these odd boxes, where I have a box that is shaped like this, and I exert some force on it to the right. And suppose the mass of the box is, suppose the total mass of this box is something I'm going to call 3m. So then I could ask, what is the acceleration on this odd-shaped box? The only forces acting on the box in the horizontal direction is your push. So in that case, I would say sum of the forces equals the mass of the odd box times its acceleration. That implies your force results in a 3ma acceleration, or that the acceleration is maybe F divided by 3m or something. Hopefully not too surprising. Of course, now suppose it is revealed to you that this odd-shaped box is actually two boxes stacked on top of one another. The bottom one has a mass of 2m, and the top one has a mass of just m. Maybe 1 kilogram, 2 kilograms, 5 kilograms, 10 kilograms, whatever. And you push on the bottom box. If they continue to move as, the same kind of solid object, like what's drawn up here, they don't slip relative to one another, what is causing the top box to move? Well, again, I could analyze the system. I have the bottom box and the top box. The bottom box is feeling a push to the right. Its own weight. It's in contact with the ground. And it's in contact with the top book, which you might imagine might be pushing, F top, might be pushing down on it as well. Then if I do a free body diagram with the top one, it has some gravitational weight, but it is also in contact with the bottom book, so there might be some F bottom. But again, if you look at this, there's no horizontal force here, so it's impossible for it to move to the right if these are the only two forces. So there must therefore be some force that is pushing it to the right, which in this case is static friction. If they're not slipping relative to one another, there must be something that is keeping them together. It has to be friction in that case. If there was no friction, you would push the bottom book and it would just slide out from underneath the top book, because there is nothing that is pulling the top book along with it. So this is kind of fun because it seems like in this case, actually, it's friction that helps the top box move in the same direction as the overall velocity. Friction is actually the reason the top box moves in the direction to the right. You might think, but you went through an entire lecture saying that friction always opposes motion, and it does. And let me try to argue why this is still an example of opposing motion. I have two books, my notebook and some, pad of paper book. And if they stay together and I push them in one direction, they move together. They move as one unit. They do not move relative to one another. Friction does want to oppose motion. So if I push the bottom book, and it were such the case that the bottom book moved while the top book stayed perfectly still, friction wants to oppose that motion where it looks like the top book is kind of moving in one direction and the bottom book is moving in the other. So friction wants to make sure that they stay like this, where the top book is kind of centered in the middle of the bottom book. So this, in order for friction to kind of undo what's happening, friction has to also point in this direction to keep the book centered on the bottom book. So in this case, if the bottom book moves to the right, friction then also points in this direction to keep it centered. This is also the idea behind the trick of pulling a tablecloth out before everything on the table falls over. Right, the idea there is that there is definitely friction between, say, a table and a champagne glass. But or I guess a tablecloth and a champagne glass. But if you pull it quick enough, which really what you're doing is you're creating a very large acceleration with the tablecloth. it will be the case that that acceleration is too large for static friction to maintain. Static friction would not be strong enough. So then it becomes kinetic friction between the champagne glass and the tablecloth, which is lower. And then as long as you get rid of the tablecloth fast enough, that doesn't leave enough, the ideal scenario is that it doesn't leave enough time for the tablecloth to pull the champagne glass with it and then therefore tip the champagne glass over. Now you have to be very careful about, what is the friction force if you want, I could ask, how large a force, if I gave you a coefficient for static friction, I could ask, what is the largest force that can be applied to the bottom box before it starts to slip relative to the top box? So therefore you have to then evaluate something like the coefficient times some normal component. But what is the normal component in this case? In this case, again, the normal component, we defined it as the contact force with the surface. Which is again why I hate normal, but this is the contact force with the surface. But in this case, for the top box, the surface it's residing on is the bottom box. So this force plays the role of the normal force in the friction equation. So you'd have to calculate what that force is using Newton's third law, because we can also identify that this and this are Newton's third law force pairs. And therefore, if the bottom box has some acceleration as a result of forces, you can solve the Newton law problems, connect them via Newton's third law, calculate what this normal component is, and then back out how, what force is too much before slipping occurs. You might try that. And then, of course, as long as friction is able to maintain this without slipping, you, of course, could go through all of this math, and you will, of course, still get that the acceleration of both boxes, if you were to calculate it numerically, is still just F divided by 3m. So good. Fictitious forces, or pseudo forces, or I don't know, make believe. Here's a scenario. You're driving a car. You're driving straight forward in your car, and you make an incredibly sharp left-hand turn. You feel yourself thrown to the right side of the car. If you had a basketball that was just sitting in the back seat of your car, it would be thrown to the right side of the car. Rather, it would appear that the basketball is thrown to the right side of the car. It would appear like you are being thrown to the right side of the car when you made that sharp left-hand turn. And it feels very real. Though after everything we've been talking about, you can now stop and ask yourself, but there are no forces that are acting on me that's actually pushing me to the right, is there? And there's not. So if you just lived inside your car and you didn't know that it was a car that was making sharp left-hand turns, you blacked out all the windows, for example, and the car was making sharp left-hand turns, you would feel yourself being thrown to the right side of the car constantly, even though nothing seems to be actually pushing you to the right side of the car. So if you try to do Newton's laws, you would say that there is some force that is pushing you to the right. Though from the point of view of someone outside the car, they would say there's nothing pushing you. So what's going on here? From the point of view of someone outside the car, if they are standing, say, perfectly still on the side of the road watching all of this happen, they would be able to conclude the right answer, in that it's not that you're moving to the right, It's that the car is moving to the left and kind of leaving you behind. I could take an example of, suppose I have a car that is making a left-hand turn. So here is kind of the front of the car. And here you are in the driver's seat. And there's your kind of path that you're making a turn. We talked about this in the last lecture. When you're making a turn, you turn the steering wheel of your car. That rotates your wheels. There is then a friction force between your wheels and the road that points towards the center of this hypothetical circle. Your car then starts to undergo circular motion. Your car starts to undergo circular motion because there is a force, friction in this case, that is causing the velocity vector of your car to move, to swing to the left. But friction is not acting on you. You are not in contact with the ground. You are not the wheel that is turned and is now, feeling a friction force. So you, by Newton's first law, have no forces acting on you. You continue just moving in a straight line. So you continue moving in a straight line while your car is turning. So notice where the green dot ends up as the car is turning to the left. You keep going in a straight line. Suddenly, you feel yourself as if you're on now the right-hand side of the car. Not because you got pushed to the right-hand side of the car, but because essentially the entire car moved to the left and you got left behind. Another example. I could take my apple. We've done this demo a bunch. I could throw it up in the air. I throw it up in the air. It falls back down. I can catch it. We did demos where if I walked forward at a constant speed, I could throw it up into the air and I would still be able to catch it. That was the ball in the cart demo. Now imagine I keep throwing it higher and higher into the air, and I'm outside and there's nothing in the way, and I keep throwing it I keep throwing it higher and higher and higher into the sky. There would eventually become a point where I throw it so high into the sky, wait around for a while, don't move. I'm not moving at all. I'm standing perfectly still. I've just thrown the apple directly up into the air and I keep my hands held out, waiting for it to fall back into my hand. But you would find instead I throw it up into the air and the apple would miss. Do it again. I throw it really high into the air, so high into the air, and then I just hold out my hands as I wait patiently. So you throw it really high, and the apple would miss. You would actually be able to see that in the northern hemisphere, here's the hint, you would notice that the apple has moved west of you. It's moved more towards the west of you, but did not fall straight back down. From your point of view, you would say something clearly pushed the apple. If it changed direction, there had to be an acceleration. It appears like something has pushed the apple to the west. But from an alien's point of view or an astronaut's point of view, they would say, no, there is nothing pushing the apple to the west. You just simply threw the apple into the air, and then you moved. But I wasn't moving, you respond. But the Earth was, because the Earth is rotating. And rotation, remember, is a change in direction. Rotation is an acceleration. So you accelerated as the Earth rotated. So it's not that the apple moved, it's you threw the apple into the air, and then you rotated away, and then the apple appeared to then continue to move in a straight line and fell besides you. And you might say, wait, the ball in the cart demo displayed that if there was motion between the cart and the cart still caught the ball. But that was the case where they were both moving at a constant velocity, a constant speed. We looked at this for an in-class demo. You all correctly, through intuition, identified that if the cart started to accelerate after the ball was in the air, the cart would not catch the ball. And that's the same sort of thing as what's going on here. I threw the apple into the air. Yes, the Earth is rotating, so there is some speed that I have initially, and the apple continues to have that speed when it's in the air, but because of the rotation, my direction changed relative to the apple. So then the apple appeared to move from my point of view. Really what happened is I rotated out of the way, and that is why I missed catching the ball. So what gives? It seems like we have contradictions here. Two different points of view are reaching different conclusions as to what forces are operating on what. From the astronaut's point of view, they would say, no, there's no forces acting on the apple. From my point of view, I said the apple clearly moved. There must have been a force that acted on the apple. So what I'm identifying appears to be a sort of fictitious force. It is called the Coriolis force. It is a force that appears to be acting on an object, even though it's really just a result of the fact that the Earth is rotating. If the Earth were not rotating, I would be able to throw the apple arbitrarily high into the air, and I would catch it. But because the Earth is rotating, when I throw it into the air, I rotate out of the way. It appears like the apple moved in the opposite direction. I would say, there's a force acting on it, which is I'll call it the Coriolis force. Coriolis force plays a very important role for, say, why there are hurricanes, for example. The rotation of the Earth underneath kind of the relatively differentially moving atmosphere. Those relative motions can cause things like hurricanes. What's happening with the basketball in the car, or the driver's seat in the car, is, again, remember the outsider said, no, this is just centripetal acceleration on the car, and then you are just moving in a straight line and getting left behind. The person in the car would say, no, I feel myself being thrown to the right. I'm going to call this the centrifugal force. Again, that is a fictitious force that it's not actually, there is no actual force that is pushing you. It's just that your reference frame, the car, is undergoing centripetal acceleration in the opposite direction. The centrifugal force is just the centripetal force in the opposite direction, if you were to measure the magnitude of these things. So this suggests something, actually, I have a demo related to that. So here I have a bucket. It is empty. And I fill it with some water. If I make this water undergo circular motion, then the rope pulls on the little paint bucket. That causes the entire thing to start spinning around in a circle, but the rope is not touching the water, and really it's the contact force of the normal force that then causes the water to start to undergo circular motion. But imagine if we were living inside this bucket, we were just walking around, we were just drifting around in the water. When the bucket starts to spin in a circle, it would be undergoing centripetal acceleration, but from the point of view of the water inside the bucket, it would feel itself press down to the edge of the bucket. And as long as you do it fast enough, there's no problem with the water remaining nice and perfectly inside the bucket without spilling, even though there are times where the water is, where the bucket is completely upside down. And it seems like gravity should just make the water fall immediately out. But because of the circular motion, or from the point of view of the water, it's feeling a force pushing it down into the bucket. It remains stationary. But this doesn't put our mind at ease because we still have the issue now where it seems like Newton's laws would give different answers depending on your point of view. The astronaut would reach a different conclusion using Newton's laws versus me throwing the apple into the air, where I would say there's a force that's causing the apple to move. So this actually gets us to the idea of the validity of Newton's laws. And Newton's laws assume what's called an inertial reference frame. Your book talks a little bit about this, I think, at the beginning of chapter 5, where they actually define an inertial reference frame as a reference frame where Newton's laws work. Newton's laws give you the right answer only in inertial reference frames. And in this case, for the sake of this kind of simplified optional discussion, inertial reference frames we can think as non-accelerating reference frames. Oops. If the reference frame you're inside the car is making a sharp turn, that's an acceleration. That your whole point of view is accelerating towards the left. Or I'm on the Earth, which is rotating. Rotation is an acceleration. So the Earth itself is a terrible reference frame for Newton's laws. Luckily, the effects are very small and hard to notice as long as we stick to, say, throwing apples up into the air, just within this room. Any sort of issues with the fact that the Earth is rotating do not become manifest. Missile guidance systems, however, that might, transatlantic missile systems or things that have to traverse long distances or long periods of time, does have to take into account the fact that the Earth is rotating as well. Or you would get the complete wrong answer. So the idea behind inertial reference frames is that these are frames where everyone would agree on the accelerations and the forces that are acting on objects. We saw this in the relative motion lecture, where someone dropped a rock off a cliff while another person was observing this entire process while wearing a rocket attached to their back, and they were accelerating upwards. That rocket's point of view is an accelerating reference frame, an accelerating point of view. And remember from that lecture, they disagreed with the acceleration that the rock was falling towards the ground. The person who dropped the rock said the rock falls at 9.8 meters per second squared. The person with the jetpack accelerating upward would have disagreed and said, no, I think that the apple or rock or whatever is accelerating at a different rate. And now that we know about forces are the cause of accelerations, they would therefore also disagree on what forces are acting on the rock as it fell. The person that dropped it would say, okay, it's accelerating at 9.8 meters per second squared. It seems like there's a gravitational force, that's mg. That is the force that's making it accelerate at that rate. Where then the person at the rocket jet would say, well, okay, I'll give you mg, but this rock is accelerating not at 9.8 meters per second squared, so there must be some other additional force that's acting on the rock. And they disagree because the person with the rocket jet who is accelerating themselves, their point of view is a reference frame that is non-inertial. So they would not agree on the forces that are acting on an object, for example. So these centrifugal Coriolis forces sometimes are called fictitious forces, which I don't really like because they feel quite real. You feel yourself being thrown. Like, I would not call that fake. It feels very manifest. But really, I think what is meant by the idea of a fictitious force is that you're trying to identify and label forces in a terrible reference frame, a reference frame that's accelerating. And you might think, well, surely we can fix this in some way. And if you do know that you're accelerating, if you do know your point of view is terrible, you can essentially take that into account when you write down Newton's laws. So suppose your frame of reference is accelerating at a rate capital A. Maybe it's a turn. Maybe you're in a car and you've just slammed your foot down on the pedal and you're speeding up. There's another example where you slam your foot down on the gas pedal. You feel yourself kind of thrown back into your seat. Nothing's pushing you back onto the seat. The fact is that your reference frame, the car, is accelerating forward and you're getting left behind. So you feel yourself thrown backwards into the seat. So if your frame of reference is accelerating with some acceleration big A, Newton's laws still work if you add in a fictitious force. F fictitious, I guess, equal to minus m, the big acceleration. In a sense, you're kind of you're adding in this fictitious force as a way to subtract out the acceleration your entire reference frame is undergoing. Let me give kind of one example of this. And this is important because there are some things where even if your point of view is crappy, you need to still reach the same conclusions as other reference frames. Suppose you have someone who is accelerating in a car forward, and they have something hanging, you might have something, a little disco ball that hangs by under your rearview mirror. So it's more obvious here. Suppose they have something that's hanging kind of on the roof of their car, kind of, down in the passenger area behind. Again, if you slam on the gas pedal, and you might have noticed this if you have stuff dangling and hanging by on your rearview mirror, if you slam on the gas pedal or you slam on the brakes, you notice that the things on your rearview mirror might move forward or backwards, even though nothing is pushing forward or backwards on the object. So you might have like a little disco ball, which will appear if you're accelerating forwards. The disco ball will appear from the person driving the car to kind of swing backwards, just like how you feel yourself thrown back into your seat. Versus someone that's watching kind of outside who they themselves are not accelerating. And their acceleration might be, is either zero, or their acceleration is zero in this case. They are in a non-inertial reference, or an inertial reference frame, sorry. Now, if this disco ball is hanging by a thread, that thread might snap if the tension in the thread is too high. Obviously, both of these observers have to agree on when the thread breaks. It can't be the case where the person driving the car says that the thread breaks, where the person outside the car says the thread doesn't break. That would be nonsense. That they have two different alternate realities of what's happening. They have to be able to reach the same conclusion. And so, maybe I'll make this observer green. So what the green observer would say is they would say, okay, I'm going to draw a free body diagram for the disco ball. It appears to be at some angle, relative to the ceiling. So there's a tension. There's gravity pulling down on the disco ball. But then I know that the car is also accelerating forward at capital A. So then I would say something like tension plus gravity equals the mass of the disco ball times big A. That is what the outside observer would say. And then they could solve for the tension. They could get the tension in the string. Where the person driving the car, if they are being careful, would say, okay, I'm going to draw a free body diagram. And I see also a tension that is at some angle, the same angle, in fact. There's gravity pointing down. And if that were it, they would reach the wrong answer because they would say the sum of these two forces is 0 because they're inside the reference frame that's accelerating. They, from their point of view, it just looks like the universe is accelerating past them. In their reference frame, they are stationary. You know, the person is not moving forward or backwards in the car. They are remaining stationary. They are not accelerating in their car. So they have to then add in a fictitious force, F fictitious. And so then they would say T plus gravity plus F fictitious equals the mass of the disco ball times the acceleration in the frame of reference of the car. But the person looks back to the disco ball, sees that the disco ball is not moving at all. They would conclude that's 0. And notice that by the definition I gave above, this is minus m capital A equals 0. Their equations ultimately end up being the same. So as a result, they would reach the same answer. Only because the person driving the car correctly realized they were in a terrible reference frame and added in that fictitious force to make everything sane. Again, this lecture is optional, so I would never ask you anything like this on the exam, but this is a college-level physics class. There needs to be some stuff that I feel really pushes your mind a little bit. So really, this is the whole idea. Like, you use this sort of approach where you can then derive the centrifugal force being just the opposite of the centripetal. And the Coriolis force is the fact that there is rotation going on underneath. But that stuff, to do that carefully and more exact, requires some vector calculus. So that's saved for upper level mechanics. So for the physics majors, that's something for you to look forward to. All right, cool. End of optional lecture.